Thank you very much, Simon, Alex, and Brian, for these very nice introductions to Marlowe and the Marlowe CLI. I thought it would be nice to play a bit with Marlowe in the Marlowe playground. And since Simon recorded his lecture, the address of the Marlowe playground has changed. So I'm using Marlowe minus playground minus staging.plutus.aws.iohkdev.io. And when you go there, you see there are several options to start or to play with Marlowe. So you can use JavaScript, you can use Haskell, you can directly use Marlowe, or you can use Blockly, which is a very nice graphical tool. So you don't need any programming experience to get started with Blockly. And that's what I want to do first. Since I recorded this demo, there have been some minor changes to Marlowe and the playground. For example, time used to be based on slots, and now it is also based on POSIX time, like in Plutus. But I think those changes are so minor that they don't matter, and almost everything that you will see in the demo is still exactly as it used to be.
This is a graphical editor, so we can just click and drop a Marlowe contract together. And as an example, I want to write a contract where there are three parties, Alice, Bob, and Charlie. And the idea is that Alice and Bob deposit an amount of ADA into the contract, let's say 10 ADA. And then Charlie decides whether Alice or Bob gets the total amount. And depending on Charlie's decision, either Alice gets 20 or Bob gets 20. And of course, there's always the possibility that one of the three doesn't play along. And Alice doesn't make her deposit, Bob doesn't make his deposit, or Charlie doesn't make his choice. In which case, everybody should just get reimbursed what they have paid up to that point. So when we start with Blockly, there is a contract and it's just a closed contract, which in this case doesn't do anything. If there was money in internal accounts, it would pay back the money to the owners of the accounts. But we want to do something else. So let's first wait for a deposit by Alice. And because that's an external action that's triggered by one of the parties, in this case Alice, we need this when construct that Simon mentioned. And we can slide that into here and we see all the slots where other things need to go. And we see some fields that we have to set. So let's start here. So we can set a timeout. So let's say this deposit by Alice has to happen until slot 10. And if it doesn't happen, we can say what should happen afterwards. And there's not really a good choice to do anything except close in that case. So in that case, nothing will happen. So we can slide that in there. So now here we say what external actions we wait for. Let's say we only wait for one action, namely that Alice makes her deposit. So we can check for actions and pick the deposit one and slide it in here. And we see a couple of slots we have to fill. First of all, who has to make the deposit? That's a party. And there are two choices, public key or role. Let's take role, because then I can just say Alice. Normally this would be the name of the role token. So whoever owns that token can incorporate that role. Okay, so Alice makes a deposit. Now the amount, that's a value. And let's say we just pick a constant amount of 10 ADA. So the amount is 10, and that it is ADA we must specify here in the currency slot. There's also the option to use other tokens than ADA, but let's stick with ADA. Okay, now there are these internal accounts that also belong to one of the parties. So let's say Alice pays it into her own internal account. So I just copy pasted this. And now we must say what happens next if Alice makes this deposit. So afterwards we want Bob to make a deposit. So I can just copy this whole when block here and slide it in here. And now change it. So first of all, I changed the timeout to 20. So to give Bob also 10 slots to do something. And then wherever I said Alice, I now say Bob. So at this point, if both these actions happen, Alice has deposited 10 into her internal account and Bob has deposited 10 into his internal account. So now we want Charlie to make a choice. So we need, this is again an external action. So again, we need a when. And I put that in here, but this time it's not a deposit. So let me delete the deposit, but let's change the timeout to 30 to give Charlie 10 slots to make his choice. And now I need a different action where earlier I had deposit. Now I pick the choice action. I can give it a name, let's say winner. I must say who makes the choice, so that's supposed to be Charlie. And now I must specify what values this choice can have. And that's numeric, so somehow, because Charlie is supposed to choose between Alice and Bob, so that's 2 choices. So I can pick arbitrary values like 1 and 2. 1 for Alice, 2 for Bob. So and that's already the default, so that's fine. So this allows Charlie to only choose 1 or 2. And then after he has made the choice, if he has made the choice, we continue. And now it depends, of course, on what choice Charlie has made. If he chose Alice, then Alice must get all the money. If he chose Bob, then Bob must get all the money. So here in this continue contract, we now can use if, simple conditional, slide that in here. So first we need the observation. So we must somehow check whether the choice was, let's say, 1 for Alice. So this is an observation, and there is value equality is one of the options. So we want to compare the choice that Charlie made with 1 or 2, doesn't matter, but let's say 1. So value, there is this one, which gives us the value of a choice. So here we need the name again. So winner was our name for that choice, because there can be several choices, so we must be able to distinguish between them. And we again need who made that choice. So this is now either 1 or 2, and we can compare to, for example, 1. So we can use the constant value 1. Okay, and in this case, so if this is true, then Charlie chose Alice. So we want Alice to get all the money. So in the then branch, we can now take a pay contract. The payee is who gets the money, and now we have 2 choices. That can be an internal account or it can be an external party. And in this case, it doesn't matter, because in the end, when we close, all the parties get the money from the internal accounts as well. So it doesn't matter. I can just pick the internal account, Alice's internal account. So let's do that. Pick Alice. So this now means that the payee is Alice's internal account. Now how much? It's this constant 10, the amount that Bob paid in. Currency is ADA. And now who pays? And that must be an internal account, because this is something this pay contract is something the contract has control over. So that's not an external action. So payments are triggered from internal accounts that are under the control of the contract. And that in this case is Bob's account. So this now says if Charlie picked 1, which stands for Alice, then pay from Bob's internal account 10 ADA to Alice's internal account. And afterwards, we can just close. And when we close, all the internal accounts will be paid to the external owners. So at this point, Alice's internal account will have 20 ADA, and when we close, she will get the 20 ADA paid out. Okay, and else, this is now if Charlie didn't choose Alice, if he chose Bob, well, then we must do the same, but with reversed roles. So let me copy paste this whole pay thing and just exchange Bob and Alice. And this should do it. Now we can, for example, look at the pure Marlowe. So this is now the value, what I did graphically as a Marlowe value, a value of the Haskell data type called Marlowe, or called contract actually. And I can send it to the simulator. And I can start the simulation. And now whenever there is a when, so when there are available actions, I get prompted which of those to take. In our case, we always only had one available action at every point. So in the first when, there are only two possibilities. Either Alice makes her deposit or she doesn't until the timeout is reached. So in this case, if we wait for the timeout, it's very boring. The contract is over, is reduced to close, and nothing happened. So if she makes the deposit, then this contract simplifies. So it's now reduced to what happens after she made the deposit. And we see now we are in the second when, where we are waiting for Bob's deposit. And again, he can choose not to deposit. So if he does that, then we see here the actions. Alice deposited 10. And then after the timeout, because Bob didn't do anything, the contract paid 10 back to Alice. Okay, of course, it's more interesting if Bob also makes his deposit. So we see that logged here as well. And now the contract has simplified again. So now we are in the when where the only available action is that Charlie chooses. So Charlie can now choose 1 or 2. If he chooses or don't do anything. If he doesn't do anything, Bob and Alice both get their money back. If he picks Alice, so choice 1, then we see that the contract pays 20 units of ADA to Alice. So she gets all the money. And if instead we pick 2, then the contract pays 20 units to Bob. So it seems to work. Let me reset this now. And let me copy this Marlowe contract and do a new project and go to the Haskell editor instead. And let's not save. And here in this Haskell editor, there's a template. Basically, all this Haskell program does is it takes a contract. This is a Marlowe contract. And then it's a simple executable, a Haskell executable that just pretty prints the contract. So all it does is it basically produces a nicely printed value of type contract. And this is then used to, for example, run in the simulator. So we should be able to simply, instead of close, paste this expression here that we got from our Blockly. Probably I should indent. Okay, and that should compile. So I can compile this. And I can send it to the simulator. And it should behave exactly as before. So Alice makes a deposit, Bob makes his deposit. Let's say Charlie picks Bob, and Bob gets the money. So there we don't really see a benefit of doing it in Haskell. We could just as well do it in Blockly. Although I find that Blockly is really only useful for learning and for writing extremely simple contracts. Because this is arguably a simple contract, and already it was quite unwieldy in the Blockly editor. And if you do something slightly more complicated, it gets really very confusing in the editor. But the point is, we can do other things in this Haskell program as well. We don't have to literally define a contract. We can use the whole power of Haskell to help us write this contract. So for example, we see there's lots of repetition because we always have these roles, Alice, Bob, and Charlie. So for example, we can define them separately and just say Alice, Bob, Charlie. The type is party, and the role constructor, we can just use this overloaded string here to skip the role constructor and just write it like this. So party implements isString, and the fromString method uses the role constructor. Charlie. Okay. And now I can replace this everywhere with those. Here as well. And here as well. And I can do the same for Bob and Charlie. Okay, I think I have all the places. Now I can do the same. This constant 10 is all over the place. So let's give that a name as well. Let's call it deposit, and that's of type value. Okay. This token empty empty, there's the ADA abbreviation for that. Okay, and there's slightly more computation duplication, this choice ID. So let's also give that a name. Choice ID, type choice ID. And that takes two parameters, the name, which was winner in our case, and the role, which is Charlie. Okay, now it's already cleaned up quite a bit. And now it's also easy to do more sophisticated things. For example, our contract is slightly asymmetric, even though it sounds like a symmetric situation. I mean, Alice and Bob are completely symmetric, but in our contract, Alice has to deposit first. And what we could do instead is allow Bob to deposit first as well. So in the outermost when, we have two cases, one where Alice deposits and one where Bob deposits. So we can, of course, just now copy this case here and paste it below and change Alice and Bob where appropriate, which is not everywhere, because in this choice thing here, Alice keeps being choice 1 and Bob keeps being choice 2. So would have to concentrate on that. But of course, it's much nicer to extract that into a helper function. So this is of type case. So let me just copy paste or copy this until there. And now make a local definition. And I don't know what to call it. Let's just call it F. And it takes two parties, the party that deposits first and the party that deposits afterwards, and it gives us a case. Let's call it X and Y and just paste this whole thing there. Okay, and now of course I am not using the X and Y, so in this case Alice was first. So Alice is X, and after Alice's deposit we wait for Bob. Okay, and this here can stay the same, this choice. Okay, and now I can replace this whole thing with my helper function and write F Alice Bob. And the advantage is that it's now easy to also add the symmetric case that Bob can deposit first. So I just add a new line with another case, Bob Alice. And if all goes well, that should still compile. And if I now send it to the simulator and start the simulation, now I have two possible actions that can happen in the first step. Alice can deposit 10 or Bob can deposit 10. So let's Bob start this time. So Bob deposits 10 and now it's Alice's turn. And if Charlie picks Alice, then as before Alice wins. So the point I'm making is that it's of a big advantage to use the Haskell editor to write Marlowe contracts in Haskell. So basically you write a program that produces something of type contract. And you can use all the features of Haskell, like local functions or whatever, to make your life easier and avoid code duplication. And in the Blockly editor, there's no such option. If we had wanted to do the same in Blockly, because there are no local definitions that you can do, you can't define local contracts or something like that. So we would have to copy paste this whole big case and then manually change Alice to Bob and Bob to Alice in the first two deposits. And we would have lots of code duplication because this choice thing here, the third one, would have been copy pasted and there would have been no way to abstract that away and only write it once. And of course you have other options. For example, we could also parameterize our contract. So for example, we could leave the deposit variable. So we could instead do contract is a function from value to contract, and the first parameter is deposit, and I delete this here. And now in the main program I can pick a value for the parameter, for example 50. And now if I compile, oh sorry, it must be constant 50. So now if I compile, I have a version of the contract where now Alice and Bob have to deposit 50 ADA each. And then the winner gets 100. And obviously I could do the same for the parties. So I could parameterize it over the three parties. Party, party, party. And then if I call those Alice, Bob, and Charlie, delete this here, then I must also be careful, and this must now depend on a party. Let's call it P. And at the appropriate spot here where the choice happens, I must say choice ID, Charlie, here as well. Okay, and now the contract is parameterized by all participants. So instead of Alice, Bob, and Charlie, I can use Charles, Simon, and Alex, and constant 100. What did I do now? Oh yes, just a parenthesis problem. Okay. And now I have Charles and Simon and deposits of 100. And Alex picks the winner. And it works as before. So it's very nice and easy to using Haskell, parameterizing contracts and saving a lot of code duplication by just using usual Haskell features like local definitions, helper functions, and so on. I could even relatively easily generalize this to more than 3 participants. Maybe there are 3 people. I could even write a contract that's generic in the number of parties. So I get a list of parties and then each of them has to deposit. And that would be very inconvenient if I had to do that by hand. But just using Haskell, it's quite straightforward. And what is also noteworthy here is that Marlowe, in contrast to Plutus, is extremely basic Haskell. So the Marlowe team made a point of only using very basic Haskell functions and features. So you don't need lenses, you don't need template Haskell, you don't even need monads. Type level programming, all of that is not present in Marlowe. It's extremely basic standard Haskell. So after what you have learned while learning Plutus about Haskell, Marlowe should be a walk in the park for you and very relaxing and simple. Of course, Marlowe is not always appropriate because it's specifically for financial contracts, But if it is appropriate, it's a very nice option because of all the safety assurances that Simon mentioned, and because it's much simpler and easier to get right than Plutus.
I also provided the code that you just saw in the demo in the Playground editor in this week's code folder. So it's in app/Marlowe. It's an executable. When you run it, you will actually see this contract that we create using Haskell and these helper functions. Building the code is easier than normally in the other weeks because we don't need nix. So a simple Cabal build will suffice.